Good morning, everybody. From the sublime to the prosaic, I'm going to sort of summarize a bit of the physics that underlies what Robin's been talking about and think about what that might be able to do to apply sense and science to traditional windows. Now, windows are probably the most complex element in the building. They do a whole lot of things. And I'm just going to concentrate largely on the blue ones, but of course we have to take account of all the other ones as well. Now, it's very easy to be reductionist about buildings. And this I found absolutely extraordinary when CIBSE published its first applications manual on Windows design. What was on the cover? Buildings with all glass and no windows. No controls, no anything. It wasn't about windows. In fact, its latest edition is simply about windows and daylight. But I wonder if this had something to do with the epidemic of glare and overheating in modern UK buildings, viz. The modern office that Robin occupied that she showed. I got a lovely picture of them in there with umbrellas, because it's the only way to keep the light off, because chinks of sun go through the internal blinds they had. And the modern movement, and particularly Le Corbusier, was all trying to make buildings rational. So instead of having an integrated window, he'd try and separate all the functions. But a sash window does so much more. I was going to talk a lot about that, but I don't need to, because you talked all about that yesterday anyway. But it is an absolutely brilliant invention. It gives you fine control. You can decide where to put the draft. You can have a lot or a little. You can have it at the top or the bottom, but the top often doesn't work very well, and I'll come round to that later. But in general, often windows that are replaced or in modern buildings lack the functionality of the sash. And it's also a problem. The sash stays in the plane. You have curtains inside, you can have secondary glazing inside, you can have shutters outside, you can do what you like, and they don't bang into each other. I mean, one modern building I looked at in the 90s, the external blinds which it had were a guillotine for the openable window. So let's just have a look. There are 4 sections on this. Keep the heat in, keep the heat out, manage air and moisture, and then join it all up in a few examples. So normally the heat coming in, you think of U values in watts per square meter per degree Celsius or Kelvin. And that, as Robin said, is a conductive bit. There's a convective bit and there's a radiative bit, and the radiative bit is quite important. And Windows have been dealing with that rather better in the last 20 years or so, with having low emissivity coatings which catch some of the radiation going out on the outside face of the inner bit of the window and send it back in again. And then you can look at what goes through the glass, or you've got the frames as well, or you've got the interactions between the glass and frames, particularly at the edges, if you happen to have a double glazed sealed unit or whatever, where the edge thermal conductance is not as good as the rest. And we're looking largely at heat loss for the UK, but of course it also reverses when the air is hot outside. And then there's the whole ventilation and infiltration bit, which I'll come on to in the later section. This is the work done at Glasgow Caledonian University for English Heritage Historic England at about in the late noughties, which I reviewed, looking at what you can do to improve a window by adding stuff. So you start with 5.8 just through the center of clear single glazing. Double glazing at the time wasn't argon filled and wasn't low E coated. And so you got down to about half with double glazing with 16 mil air gap. Sort of 16 to 25 mil air gap, it doesn't make much difference on the double glazing. If you go less, it conducts more. If you go more, it convects more, because if you start having too big a gap, there's a convection cycle in there, which it certainly does under laboratory tests. reduce the efficiency of sealed double glazing units when they go over above about 25 mil air gap. And if you go down to triple glazing, you get down to about a third of it with 260 mil. But it's a very, very chunky, heavy thing, and it really doesn't marry up at all to the very, very non-chunky, fine sight lines that we often get on traditional British windows. So then we bring in the low E, and with argon fill, and you're down to about a quarter through the center of the thing. And if we go to slimline, not quite so good. Now, the problem with argon fill in slimline is, argon fill in anything, is the argon fill gradually comes out through the perimeter seals. So in about 10 to 20 years, a lot of it's gone. So a lot of what it's sold on is no longer there. You know, the slimmer the gap, the more likely it is to get out earlier. So there's an issue always with modern products that they're great, but will they last? So here's the report on the sash window work, and on the right is a similar report on metal window work, which I won't talk about today. So what you've got then is, if you add the frame, a wooden frame is more insulating than single glazing, so you've gone down from 5 and a bit to 4 and a bit. So, and this is a window that was taken out of a building, put in a climate chamber, 2 climate chambers, a hot one and a cold one at Glasgow Caledonian University, and then you look what happened when you played around with it. So if you start off, it doesn't change, obviously, the total value, whether you've repaired the joinery or added draft proofing, but I'll come to other things it does later. But if you start adding curtains, it makes quite a difference. And if you start closing your shutters, you're actually better than some of the double glazing. But mind you, sometimes you want to see out the window, so that's not terribly clever. But you can have a roller blind, but you also have reflective roller blinds. You can have reflective roller blinds you can see through. So, and it also helps to keep the heat out. So there are clever things you can do. So, you know, all the sort of reflection or insulating, you can get much the same result by either dealing mostly with the convection or mostly with the radiation. And then if you put in secondary glazing, you get a better result, and then you can do what you like with it, except that a lot of secondary glazing isn't terribly functional. So it inhibits your use of the primary window. It inhibits your maintenance of the primary window. So some are very good, but you need to always think about that, because sometimes you find secondary glazing reduces. And vacuum secondary glazing, we thought, well, if you're going to spend all the money on doing this, it might be useful to put in vacuum glazing, which is only 6 millimeters thick, or 8 millimeters in a toughened version, which you can now get now, but we couldn't get in 2009. Now, Salford did some work on their energy house and said, this is all very well, but it's in a climate lab. And often in British buildings, you have a radiator under the window. And of course, you have curtains over the window and a radiator under, and the air goes up behind the curtain. You might get quite the opposite effect. So you have to be a bit careful. In all this stuff, there's a subtlety. These are only just order of magnitude figures. In a particular context, things may be different. Now, of course, as Robin said, the Victorians knew all about this, and they had things. Now, the interesting thing, Robin's got a door curtain in a flat in London. And you wouldn't expect it to make a massive difference in a corridor, but it does make a massive difference. And I haven't yet got a time-lapse IR camera on it to find out exactly what's happening there. But it's a combination of radiation and air movement, but also diffusing the drafts that come in. So they end in a little pocket round the door and actually help to reduce the heat transfer out rather than whistling along the floor and into the sitting room.
It's even better in summer.
Sorry?
It's even better in summer. It's hot like this.
Oh, really? Really? Well, you have the direct experience. I must get that camera rigged up. So, a window is also, not only lets the heat out by conduction, which is what you calculate, but it affects thermal comfort by means of how hot or cold the internal surface is by radiation. So here we are in the test lab, and it's 22 inside and 2 degrees outside. And guess what? The glass is halfway. That's a lot halfway below the room air temperature. So even though the room air temperature's right, this thing is sucking heat out of your body the closer you get to it, and also creating downdrafts. Now, if you start adding things, as in the previous agenda, it starts getting better. The shutter's not quite so good, and the shutters can leak a bit of air too, so they're probably not quite as good as the other things. And the secondary glazing is good too. So, and also working with selector glaze in UCL about 15 years ago, we found that a low E coating on secondary glazing did help to reduce the heat losses quite substantially from sort of the high 2s to the high 1s. And Pilkington allowed the glass to be sold, whereas previously it only allowed it to be sold into sealed units. Okay, keeping the heat out. It's a really, really big problem. Here's some stuff just this year, a public sector report, two actually, one from Climate Change Committee a couple of years ago and one public health impacts of heat. It takes a long time for the penny to drop. The UK isn't only cold. And most of that's about direct sun, as Robin said. This was sun when I was preparing these slides in London on the 25th of this month. So that was the measured sun in London then by hour. So it's biggest at midday, and of course it's not very much at night. But it's really, really complex how it comes through windows, because it depends not only on the angle at which the sun hits it and the reflectivity of the glass and the transmittivity of the glass. And then if you're going through multiple layers, there's a whole lot of shuttlecock heat transfers. It absorbs, it re-radiates, it reabsorbs, it re-radiates it sometimes. Some of it goes straight through. But also ground reflection, so where the sun's falling. And then there's the geometry of your shading system. So, you know, if you want to do this precisely, it's really, really complicated, but I'm not going to do it precisely. Essentially, what you get as a sort of rough rule from some work done, I think this was in Berkeley, is that you start off, this is direct normal incidence when it's going through the center of the glass at 90 degrees. If you start going to summer high sun, then 2/3 of it bounces off and much less goes through. But you can see interior, it takes a bit off, but not very much, 75 to 60, unless it's shut, and then you're not getting the light. And if it's opened a little bit, then you don't get much of the thing. If you have a reflective blind, you get down to about a quarter of that. External blind, you get down to 20% or sometimes less. You can also do clever things with glazing that they often do in modern highly glazed buildings, where you have a selective coating which lets twice as much light through as it lets heat through. So there are a lot of sort of highly glazed buildings which do have quite a bit of solar control, but of course you can't change it when things are changing. And if you have primary and secondary glazing, the blind between the inner and the outer can be really, really useful, because you can decide whether you want the heat on that blind to come into your room or go out of your room. So there are ways of getting better performance from secondary glazing and mid-pane blinds than you might get from a total replacement. You get these sort of sealed units now with a blind up the middle, but of course they're a total consumable. Now, historically, as Ron said, I just went round the other day in my neighbourhood seeing what I could see. And this is the terrace in Camden Town. There are lots of vestiges of these windows and even more of fixings and things. And here's Robin's catalogue page, just to give us a link. And here is a street in West London. It's not actually in a conservation area, but further down the street is in a conservation area. And the left one has got dropping blinds, and here they are down. Now, as conservation officers, would you allow that or wouldn't you? Because if a few doors down the street, it would have been a conservation area. And this is me. Linen sheets, 37 degrees outside, then it's 40. Doesn't go above 27 inside. It would have been up at 30 if it hadn't had the sheets on, but cross ventilation at night. So you can see when it comes down at night, the green one is the room you can see. The coloured ones are the ones for rooms lower down, which have smaller windows and more thermal capacity. So lots of really simple, basic things you can do to get yourself out of trouble. Air and moisture. Again, You need a whole building approach. It needs to be integrated and then integrated with the design and use of the window. And you got to provide air for people, got to have enough to breathe. That's not usually really important unless it's the black hole of Calcutta. It usually doesn't go that high that you're going to die from it. It's the pollutants that are important, and the excess heat, and the excess moisture from people, but particularly all the machines they use to bathe and wash and things these days, and to control the moisture balance between fabric and the air, which a lot of traditional buildings are much better than doing, and modern buildings and finishes because of their breathability to moisture, so they act as a sponge. And so what you need to do is have some background ventilation to help keep things sweet, which traditionally could often be with the windows shut because it all leaked enough anyway, but that changes. You need to suck moist air out of concentrated places where you can as soon as possible so it doesn't go around and give you problems elsewhere. And sometimes there's an issue. You've been away and the building's shut up and it's really hot, or you've burnt the thing, or you're having a party or something. You really need to throw the windows open. Often that is not afforded either in modern designs or in old designs that have got painted up or dealt with in some other way. And night ventilation can be really, really important for keeping summertime temperatures down. And this is really difficult if you're in a southwest facing flat, single aspect with tilt and turn windows that you can't turn because of the security or the noise or something outside. So you often find the replacement windows are much less good at doing all of these things than the original ones, which we need a mechanical system instead. So this is a school down the road from me, and they've replaced their sashes with open outs, but you're only allowed to open them 100 millimeters under regulation because the people might fall out. But the 100 millimeters is nearly always 100 millimeters of opening rather than 100 millimeters of clear opening. And certainly for modern chunky windows, they sometimes don't even clear their frames at 100 millimeters, certainly don't clear their reveals. So you go from having the square meters of area calculated by the engineers to a little slot. So these things overheat nightmare. Now, why do you need the 100 millimeter restriction on the upper window? You don't, but managers often do it everywhere. Sash window, you have an opening stop on the bottom bit that stops it at 100 millimeters, and you do what you like with the top bit. So you still get an awful lot of ventilation with the safety too. Oops, pointing it the wrong way. And I even find an inhibiting factor here. I don't know whether you find it in the room, you know. Don't leave the windows open when you're out because the pigeons will come in. So when I came into my room, which was in the roof over the dining hall, it was sweltering the other day. You know what, I could only open this window about that much because it hadn't been lubricated or it's painted up or something up above. So, you know, these things are absolutely crazy. But in commercial buildings, I've seen many buildings like this where people are saying we need to put in air conditioning or something, and they don't. They just need to get the building to work. But we have got other horrors. We've got insurance companies which say you can leave the buildings overnight when you're designing the thing, and then say you can't when you're actually in there. There are cleaners and security who want to shut the windows after they've been round. In one office in Edinburgh, we did a POE on. It was squirrels. They couldn't open the windows for the night ventilation that the designers had. In India, it's monkeys. And we know about painted up. Now, what you find with a Glasgow window is that if you repair the join, as found, 2/3 of the heat losses through this window were through air leakage. By the time they repaired the joinery, it was about half. But if you add draft proofing, you're suddenly down to a very much lower proportion, and you may not have enough air. So you might need to introduce a trickle vent, introduce vacuum ventilation, maybe from another window to get that working. Because this is a sort of cheap temperature, humidity, CO2 detector, and AeroNet one. And a sort of rule of thumb for acceptable air quality for people is 1,000 to 1,200 parts per million average. Oops, it's gone up to 1827. But not only got up to 1827, the humidity has gone up to 86. So there's something very wrong. And this is what happens if you don't cope with ventilation when you improve your windows. Now, this monitoring, I think, could be really, really helpful in risk management. When we did studies which turned into the STBA guidance wheel for historic England in the late noughties, we found that owner-occupiers could cut corners very successfully in bringing their buildings up to a higher energy standard. But of course, social landlords didn't dare. So they had to throw the book at it in terms of technologies. And then often they couldn't quite afford to have the technologies in the right state. So they got vandal engineered down. And they couldn't afford to manage and maintain the technologies. So there's a real issue here, because for legislation, you can hardly say things are different for owner-occupiers and as in social and rented housing, but actually they are in terms of the way the people can interact with the building. So now to add everything up and put it together, we need something like an integrated, proportionate, sensitive, people-first, whole building and system approach, blah, 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 but I tried to get it all in one heading. And what you need to do is windows need to let things in when they're nice and keep things out when they're nasty. So that applies to all these things, including the animal kingdom, so you can have friends or you can have vandals, or you can have burglars and you want to let one in and keep the other out. And you have insects, and whatever. You have the pigeons here and the monkeys in India. So my colleague John Dollard, the engineer, said, what you need to do is get diodes right. You need to think electronically. You have something that sometimes lets the electricity through and sometimes doesn't. Now, this is the STBA green wheel I mentioned. And this came out of the terrible green subprime deal, as I called it, that the government came up with in 2011. Or was it 2012? I think it came up with it in 2011 or in 2012. Which was all getting grants or expensive loans to do things to a building based entirely on an energy-saving menu and nothing to do with whole system performance. So the idea of this was to give people access to material that might affect them if they thought of any intervention. So if you did a window, for example, I think this was a window replacement, suddenly the green, amber, and red lights come up all amber and red. We're a little bit about technical performance, we're a little bit worried about cost effectiveness, and we're terribly worried about heritage value. And then that started interacting with, well, if your window's really well insulated and draft proof, then your relative humidity might go up, and then you might get condensation problems somewhere else. You might get that mold. Also, or your surface temperature differences between your reveal and your window might become more extreme, and your reveal might start getting into a problem. And then also, ventilation needs to be taken account of over here. And also, there's another thing to heat generation. If you reduce the heat loss from your windows, you may not need to replace the boiler with that as big a heat pump as you think you need or whatever. And it goes across to other things. How does it relate to chimney ventilation? Chimney ventilation might be quite useful if you've sealed your window up a bit, or maybe it wouldn't be. Fabric first is something that's been a mantra for the sort of deep retrofit guys in particular. Now, it really should be for new buildings. You want to get rid of demand by doing as much as possible. But for existing building, it's really the other way around. It's fabric last. You want to work out from the fabric. We want to work out from the people, not in from the fabric. And also, times have changed in the last 20 years. Electricity has got much less carbon in it. So all of a sudden, getting off fossil fuels means much more getting off gas, rather than, when I first started in this area, electricity had 4 times as much carbon in it as gas. Now it has less on average, and sometimes very little when the solar or wind are blasting away. And so somebody from Octopus, but of course he would say that, says fabric fifth in some of his talks, but they're worth looking at. I don't agree because, as you will see on the next slide. And we maxed out our carbon budget, so we can't really spend vast sums on damage limitation, which may also turn a capital good into a consumer good. And as Bernard Fielden said, you know, things that are marketed as maintenance-free often mean you can't do anything about them when they start to go wrong. So we've got sort of people-first comfort. I think I'm getting close to time now, so I won't do this, but there's a whole lot of stuff. There's a whole talk I've given on this, which is referenced at the bottom, about what you can do to improve performance by working from people and physiology, etc., out, as Robin has also introduced. And it's much quicker and much cheaper, and it's reversible. So, by all means, start with the fabric when you're improving windows, but not by throwing insulation and stuff at it, by finding out how it works, whether it needs maintenance, what occupiers think about it, and how to sail your building, as Robin says in some other talks, particularly on some work she and others are doing with churches in the Sheffield diocese at the moment. And if you really want to upgrade, you can go from the simple through the low cost, through the reversible, slightly higher cost, to replacing the glass, to replacing the window. So I'll just finish off with a few examples of this. This is my sitting room, and it's got secondary glazing, but you can't see it because it's magnetically attached. Now, I want to draw attention to another detail on this sash window. You see the black staff beads. 50 years ago, the window was all painted up. I took them out, I took them down to the workshop, and I put back stained staff beads and parting beads. And essentially, every time it's decorated, they're all screwed in with brass screws. When every time it's decorated, you take those out, and then you don't paint the window up. So the window, and the window's also got draft strips, it's all perfectly offerable 50 years later with very little maintenance, except painting about every 10 years. But if you're sealing the window up, of course, you have to be careful at making sure this room has 3 windows, only 2 of them are treated. The other one and the fireplace chimney and various other things provide enough ventilation. I know I've been monitoring the CO2. There was a report, The 40% House, published in 2004, I think, said, if you can't get the carbon down to 40%, you need to knock it down. And so I started working on ways of making retrofits better than new. And one of them was vacuum secondary glazing. And I worked with Rob Pruitt, who's talking later, to design this timber vacuum secondary glazing. And one of the ergonomic things about this is on the outside, you need the upper sash out to weather. On the inside, you need the upper sash in so you get your fingers on it. Selector Glaze does it that way, but lots of people don't, and it makes an enormous difference to operability. And here it is. Interestingly, the parting bead was 35 mil on the design. It was too heavy. I took it down to the workshop and planed it down to 30 mil. It's really important, these tiny details. And also, you can suck air in between primary and secondary windows, and if you're reasonably airtight, a bathroom fan or whatever can suck it through, and in the winter you can pick up the heat that would have gone out through the inner glass and get the U value down to about 0.1. There's research to prove it. And here's some old classic double glazing. Those are the English Heritage offices in Swindon, in Brunel's own design department at the Swindon Railway Works, where they were there for noise. But the nice thing is you have a double window. You can have them hit and miss, and you can also line the reveals. So there are ways of dealing with noise. You could put insect screens in, the traditional double fenster in everywhere in Germany and on the continent. Vacuum glazing at the BRE stables, primary glazing. You can hardly see it. There's a little spot on the Spacia glass, but on Finio glass you don't even have the little spot where the I didn't show the photo here, but they also did glazing in double glazed unit, reglazing of them, and the comparison is enormous. You can't really see that this is anything other than single glazing. Unless you look very close, you see the tiny little spots along there, but you only see them if you're looking for them. This is quite a clever one in Wels, Austria. It was an industrial building with metal windows, and they left them as security grills, but put triple glazing open in on the inside, on a near passive house refurbishment. This is a house just down the road from the one in Lena Gardens I showed you with the external blind, which has been refurbished, certified passive house. And it's the one on the right in the middle, not the one on the left. And you can't tell the difference from the outside, but you can tell the difference from the inside, because instead of having 6 ways of opening the window, you've only got one, and you can only either tilt it in or turn it in. But it's got mechanical ventilation and heat recovery. But I hear they were thinking of doing a bit more because it gets a bit hot in the summer now. So, should we prioritize heritage buildings within the energy efficiency and climate policy as a EU policymaker says, or has the policy got just as much to learn from us? Thank you.